Voyager 1 did not send humanity coordinates pointing toward a mysterious planet or some hidden object drifting through deep space. What it sent back was far more difficult to visualize. Measurements from a region where the space around our solar system begins to behave in ways that cannot be seen with ordinary cameras. There were no photographs of a strange world. No glowing structure appeared in front of the spacecraft. Instead, Voyager transmitted numbers describing magnetic fields, plasma activity, particle conditions, and its position more than 15 billion miles from Earth. Buried inside those measurements was evidence of an environment that looks empty from a distance, but is actually filled with subtle physical activity. That is what makes Voyager 1's journey so remarkable. The spacecraft crossed beyond the heliosphere, the enormous region dominated by the Sun's solar wind and magnetic influence. For decades, Voyager had been traveling outward through the solar system. But after crossing that boundary, it entered a completely different environment, interstellar space. And this changed what the spacecraft was able to tell us. From Earth, the space between stars appears almost completely empty. There is darkness, enormous distances, and seemingly nothing to touch or measure. But Voyager discovered that this emptiness has properties of its own. There are particles moving through it. Magnetic fields pass across it. Plasma can become denser or thinner. Waves can travel through that extremely thin material. So the mystery was never really about an object sitting somewhere in the darkness. The mystery was about the darkness itself. Voyager 1 had not been taking pictures for decades. Its cameras were shut down after the famous 1990 image that showed the planets of our solar system from a distant perspective. Power and computer resources were needed for the spacecraft's much longer journey into interstellar space. That means anything Voyager detected later had to come from its scientific instruments rather than its cameras. A measurement could reveal that something had changed around the spacecraft. A magnetic reading could show that the surrounding field was behaving differently. A plasma measurement could indicate that the density of the material around Voyager had increased. The spacecraft was no longer looking at the universe from a distance. It was traveling through the environment itself. That distinction is incredibly important. Imagine trying to understand an ocean while standing on a beach. You can observe its surface, study its waves, and build models of what may be happening below. But Voyager is doing something completely different. It is actually moving through an invisible cosmic ocean and measuring the conditions around itself. The material in this ocean is incredibly thin compared with anything we experience on Earth, but it is not non-existent. Interstellar space contains charged particles, magnetic fields, dust, and plasma. These ingredients can interact with one another, producing changes that a spacecraft can detect even though human eyes could never see them. Voyager's plasma wave instrument became especially important because it could detect oscillations in the plasma surrounding the spacecraft. These weren't sounds in the normal sense. There is no atmosphere in interstellar space carrying sound like air does on Earth. Instead, the instrument detected physical waves in charged particles and converted those changes into information that scientists on Earth could analyze. The result was surprising in a different way. The void was not truly silent. It had measurable activity. And that activity helped scientists understand that Voyager had entered a denser interstellar environment beyond the heliosphere. This gave researchers something far more valuable than a mysterious photograph. It gave them evidence. Each measurement became a small piece of a much larger picture. A location could be connected to a plasma reading. A plasma reading could be compared with magnetic field measurements. Over time, those observations could help scientists understand what the boundary of our solar system actually looks like. The heliosphere itself is not a solid wall. There is no giant barrier surrounding the planets. Instead, it is a huge region created by the outward flow of the sun's solar wind and magnetic influence. But there is another question hiding inside Voyager's measurements. If the spacecraft is detecting changes beyond the heliosphere, could those changes help us understand the shape of the solar system itself? For most of human history, we imagined the solar system as a collection of planets orbiting the sun. The sun was at the center, and everything beyond the planets seemed like empty space. But the sun's influence extends much farther than the orbit of any planet. The solar wind continuously flows outward from the sun, carrying charged particles and magnetic fields into space. Eventually, that outward flow encounters the material between the stars. The result is a huge region of interaction called the heliosphere. It is often described as a bubble, but it is not a perfect sphere. Its shape depends on the balance between the sun's outward pressure and the surrounding interstellar environment. As the sun moves through the galaxy, the outside environment pushes against this enormous region. Magnetic fields and particles interact with the solar wind, creating a boundary that can change and shift. And Voyager is giving scientists a rare opportunity. Instead of observing this boundary from inside, Voyager crossed it. That means the spacecraft can provide information from the outside of the sun's protective region. Think about how unusual that is. From Earth, scientists can observe the sun and everything around it. They can study solar wind, monitor solar storms, and build computer models of the heliosphere. But those observations still come from within the system. Voyager gives them something different. It is a tiny scientific laboratory traveling through the region beyond the heliosphere. Its position tells scientists where a measurement occurred. Its instruments tell them what the surrounding environment was doing at that location. Together, those pieces of information can become part of a map. But there is an important problem. Voyager cannot see the entire map. It is traveling along one narrow path through an enormous region. Imagine trying to understand the shape of a gigantic cave by walking through one tunnel with your eyes closed. Every change you feel tells you something, but you still cannot see the whole structure. That is essentially the challenge scientists face with Voyager. A measurement can tell them what exists along the spacecraft's route. It cannot automatically reveal what is happening hundreds or thousands of billions of miles away in another direction. This is why Voyager 2 is also important. Having another spacecraft travel through a different path gives scientists another set of measurements. Comparing observations from separate trajectories can help researchers determine whether a feature is local or part of a much larger structure. The goal is not simply to find something mysterious. The goal is to understand the environment surrounding our solar system. And the deeper scientists look, the more complicated that environment becomes. The interstellar medium is incredibly thin, but it contains material. Charged particles move through it. Magnetic fields stretch across it. Waves can travel through the plasma. These features can interact with the heliosphere and influence its shape. So the boundary Voyager crossed is not just a line on a map. It is a region where two different environments meet. Inside, the sun's solar wind dominates. Outside, the interstellar environment becomes increasingly important. Voyager's instruments can detect the transition through changes in the surrounding plasma and magnetic fields. That is why the spacecraft's data is so valuable. A telescope might show scientists a distant star. Voyager can tell them what the space around the spacecraft itself is like. Those are two completely different kinds of observation. One looks across space. The other travels through it. And this distinction becomes even more interesting when scientists examine plasma waves. The word wave can make people imagine sound traveling through air, but that is not what Voyager detected. There is no ordinary atmosphere surrounding the spacecraft. Instead, the plasma wave instrument detects changes in charged particles. Those changes can reveal information about the density of the surrounding interstellar material. In simple terms, the instrument is sensing how the environment behaves. When the density changes, the plasma responds. When disturbances move through the plasma, the spacecraft can detect them. And when those measurements are connected to Voyager's location, scientists can begin building a timeline of what the spacecraft encountered. This is where a single coordinate becomes much more useful. One coordinate is only a location. A sequence of coordinates combined with measurements becomes a journey through an environment. It can show how conditions changed as Voyager moved farther from the Sun. It can reveal whether the surrounding plasma remained relatively stable or whether it fluctuated. It can help researchers investigate whether the structures they detect are temporary disturbances or long-lasting features. And that is why Voyager's mission continues to matter decades after launch. The spacecraft is providing observations from a region no human spacecraft had explored in the same way before. But Voyager is not immortal. Its power supply is slowly declining. Engineers have had to make difficult decisions about which systems can remain active and which must be switched off.